Hello everyone. In this lesson we're going to learn how to find the trigonometric function values of non-acute angles. We've already dealt with acute angles. Now we're going to look at non-acute angles. Some of the topics we'll look at are reference angles, special angles as reference angles, and determination of angle measures with special reference angles. We'll start with the concept of reference angles. If you're looking at an angle theta, which is between 0 and 360 degrees, so it could be a first quadrant angle, a second quadrant angle, a third quadrant angle, or a fourth quadrant angle, then what we mean when we refer to the reference angle for theta, which is usually denoted using this notation, theta prime. That's how you read that, theta prime. Then the reference angle is the small positive angle, the acute positive angle that the terminal side of the angle makes with the x-axis. Now, notice that in the case of a quadrant 1 angle, the reference angle and the angle will be the same. However, if you go to any other quadrant, they won't be the same. Look at a second quadrant angle. Notice that this is the terminal side of that second quadrant angle, and the smallest positive angle that the terminal side makes with the x-axis is this angle right here. So this is what we refer to as the reference angle. Notice that in this kind of a scenario, for second quadrant angles, we can get the reference angle by subtracting the angle itself from 180. Okay, because from here all the way to here is 180. So how much is that? That's just 180, take away the original angle, right? For a third quadrant angle, notice that if this is the terminal side, then the acute angle that it makes with the x-axis would be this angle right here. So that's what we refer to as the reference angle for this angle theta. And notice that for finding this kind of a reference angle, we would have to have a different formula. In other words, we would have to take the angle itself and subtract the 180, the half circle, from it. Then we end up with the reference angle. So be careful, that's a subtle difference, but it's important. So for this reference angle, we have to take the original angle and subtract 180 from it. But for this one, notice it's going to be 180 minus the original angle. Make sure this makes complete sense to you visually, and then you won't really have any problems as we proceed. Notice that for this fourth quadrant kind of an angle, here's the terminal side, and the smallest acute angle that it forms with respect to the x-axis will be right there, right? So notice that to get this reference angle for a fourth quadrant angle, we'd have to take the angle and subtract it from 360, because notice from here all the way around is 360. So how much is this piece? Well, that's 360 minus the original angle. So these four relationships show us how to find the reference angle for any angle between 0 and 360 degrees. What if the angle is larger than 360 degrees? So for angles alpha greater than 360 degrees, no problem. In order to find the reference angle for an angle that is larger than 360 degrees, we're first going to find a coterminal angle, which always exists, theta, which is going to be between 0 and 360, and then we'll proceed with finding the reference angle. So very simple. Okay, for our first example, we're going to find some reference angles for these four angles. Notice that a 40-degree angle is a first quadrant angle, so of course the smallest angle, the reference, and which we call the reference angle, which the terminal side makes with the x-axis, is going to be the angle itself. So in the case of a 40-degree angle, which is depicted here, notice that the reference angle is 40 as well. It's just itself. Now for a second quadrant angle like 140 degrees depicted here, remember that the rule is that we're going to take 180 and subtract the original 140 from it to get 40. So for a second quadrant angle, you just take the angle, go 180 minus the angle, and you end up with the reference angle right there. For this third quadrant angle, which we've depicted here precisely, notice that we're going to have to do the opposite. We're going to take the angle and subtract 180 from it. In other words, here's the angle. If we take away 180, we'll be left with what the reference angle is, which is going to be that acute angle right there. So we basically have to do 240, plug it in here for theta, minus 180, and that's where we get the 60 for the reference angle. And for this fourth quadrant angle, we have this scenario which we saw on our last screen, and notice that for these we have to use this formula. So we're going to take the full circle, take away from it the original angle. So in this case 340, so 360 minus 340, this 20-degree angle here will be the reference angle for a 340-degree angle. So make sure you're comfortable with these before we proceed. For our next example, we're going to look at a couple of angles whose measures are not between 0 degrees and 360 degrees. And if you recall, what we need to do with these types of angles is we need to first find an angle that's coterminal with them, which is between 0 and 360 degrees. So the first graphic here is for demonstration purposes only. It's not a mandatory graphic, but it really depicts what is involved here. So when you want to generate a 2000-degree angle, of course you always start in standard position with the positive x-axis being the initial side. Then you start your rotation and you go around enough times till you get to 2000 degrees. Now that could be really a tedious task. So there, we have a nice way of determining just exactly how that's done. So what we do is we go ahead and we take 2000, we divide it by 360 to see how many full revolutions are hidden inside 2000, and we can see there's 5.5, basically slightly over 5.5. So that means you start here, you go full circle 5 times, and then another slightly more than another half a rotation, right? And that makes sense because that's where you end up. So now we would like to know what is the smallest positive angle which is coterminal with 2000. So to do that, remember, all we have to do is take 2000, now that we have figured this out, and we're just going to take away 5 full revolutions. So 2000 minus 5 times 360, and we see that 200-degree angle, a 200-degree angle would be coterminal with a 2000-degree angle. So in other words, all we have to do now in order to find this reference angle, remember the reference angle is this small acute angle that the terminal side makes with the x-axis. So notice all we have to do now is find the reference angle for a 200-degree angle, because as far as the shape of a 200-degree angle and a 2000-degree angle, they look exactly the same insofar as the initial and terminal sides are concerned. What is really different is this arc graphic, which shows you how many rotations are needed to get to the terminal side of 2000 as opposed to the terminal side of 200. But nevertheless, the angles, if you only look at the initial and terminal sides, they will look identical, right? So if we find the reference angle for 200-degree angle, we've also found the reference angle for a 2000-degree angle, which of course, as you know, this falls into this type, the quadrant 3 type. And to get this theta prime, all we have to do is we have to take the angle itself, in this case 200, and we have to subtract the 180 from it, which is that much. That will leave us the reference angle. So basically, now substitute instead of theta 200, so you get 200 minus 180, which is of course 20 degrees. So the reference angle for a 2000-degree angle is a 20-degree angle. All right, let's look at this next one. Let me move the calculator to the other side. All right, this one is negative 3640 degrees. So notice for this one, since it's negative, you actually start with the initial side on the positive x-axis, and then to get to the terminal side you start rotating in a clockwise manner, not counterclockwise, such as in this case, which has a positive measure, but this one is negative. So, and remember, the negative direction for angles is the clockwise direction. So we want to know how many times we have to go around, right? So what we do is something similar, except we have to adjust for the fact that it's negative. So however many 360s we get in there, we're going to add the multiple of one more than that. So let's see how that works. So let's just, we don't need to worry about the sign at this point. Let's just take 3640 divided by 360. We notice we get 10.11. Now, if this were a positive 360, I would take away 10 360s from that to get an angle between 0 and 360. But since it's negative, I start with negative 3640, and I'm going to actually add 11 full revolutions because I want to get a positive angle between 0 and 360. So we're going to go 11 times 360. We always do that when the original angle is negative. Once we find how many full circles are hidden inside that, full revolutions, we add one more. In other words, we round up is the easiest way to think about it. We always round up when the initial angle is negative. So we end up with 320. So that means this complex looking angle, right, negative 3640 degrees, is coterminal with a 320 degree angle, which looks much simpler. It's just like that, right? So if we can find the reference angle for this, we have also found the reference angle for this original angle, right? So notice that we want to get this angle right here. That's the reference angle, and that falls into this category, right? The quadrant 4 category. And that is going to be requiring us to start with 360 and take away the original angle here. Well, this angle we mean by the original angle at this point, now that we have found the positive coterminal angle. So we just do 360 minus 320, which gives us 40. So the reference angle for a negative 3640 degree angle is a 40 degree angle. That's how you handle finding reference angles when we're dealing with angles whose measures are not between 0 and 360. And that's all there is to it. Make sure you totally understand these because they're going to play an important role for us before you proceed. All right, so basically to find the trigonometric function values of any non-quadrantal angle theta, we need to follow a very simple procedure which involves reference angles. So let's take a look at that procedure. To find the trigonometric function values of any non-quadrantal angle theta, we're going to use this procedure. If the angle has a measure which falls between 0 degrees and 360 degrees, we're going to move on to step 2, which is simply find the reference angle theta prime for the angle from step 1, find the trigonometric function values for the reference angle theta prime, and then just adjust the signs, right, depending on the quadrant where the terminal side of the original angle you were dealing with falls. Okay, now if the angle is greater than 360 degrees, or if it's less than 0, what we're going to do is we're going to add or subtract as many multiples of 360 as we need to, so that we find the coterminal angle theta as we did in the previous couple of examples, and then we proceed with the same few steps after that. So very, very simple if we know how to find the coterminal angle and the reference angle. So that's why both of those procedures are extremely important. But once we do that, we can find the trigonometric function values for any non-quadrantal angle. Of course, at this time, we're going to keep our focus on the nice ones where we already know how to compute, right? Those values. That means angles related to either 30, 60, 90 triangles or 45, 45, 90 triangles. Later on, we'll find procedures for handling some other angles, and on some it'll just be forced to use a calculator, which is fine as well. But any angle that's related to these so-called nice angles, such as 30, 60, 90, 45, 45, 90, needs to be handled by hand using the procedures that we'll outline in this video. Okay, we need exact values for those, not calculator generated values. So now we're going to practice finding the exact values of the trigonometric function values for special angles related to those three angles, right, without using a calculator. All right, so for this problem, we're going to find the values of the 6 trigonometric functions of a 240 degree angle. So the first thing we'll do, I've done this here using technology to make it look nice, but you can easily do this by hand. You just go ahead and draw. Let me demonstrate to you why I use technology for your sake, because looks a lot nicer than I would do. But this is what I would be drawing if I were doing this by hand, right, myself on a test situation or homework situation. So 240 degree angle, I know if I start here, it's just going to be 180, and I need to go 60 degrees more. So I know that if I come all the way here, that'll be 90 degrees more. So 60 will be shy of that. So I know I need to go to about here, like so. So there we have it. So this is the angle. Now you see this circle, we usually get this, it's called the unit circle. We'll study it in detail later. So for our purposes right now, it's not doing a lot for us, but just looking at the angle itself, notice that this is the kind of sketch I would expect to see from you when you're doing a problem like this. All right. So what we need to do is we need to find the reference angle, right? So let me go ahead and get rid of that now that you can see. Now the reference angle is actually going to be this angle right here, right? And if you recall, this is going to be a third quadrant scenario where we're going to take the original angle and take away the 180 from it to get the reference angle, right? So if theta, the original angle, is 240, then the reference angle here is going to be 240 minus 180, which is going to be 60 degrees. I'll show you the graphic that we had before. All right, so here we have it. See, that's a Q3 scenario. So to get the reference angle theta prime, we need to subtract 180 from the original angle, and that's what we did here. Okay, so 240 minus 180. On a test situation when there is a lot of stress, I always recommend that you go ahead and double check your basic arithmetic on a calculator. So here we have 240 minus 180, and we do indeed get 60. So what's the significance of that? Well, the significance of that is that all we have to do is go ahead and find the 6 trigonometric function values for 60, which is the reference angle, and then just adjust the signs. Now remember, this angle has a terminal side which falls in the third quadrant, where both the x and y values are negative, right? So if we just, since it's a 60-degree angle, the easiest way to deal with that is using the reference 30, 60, 90 triangle, right? Where we know, if you remember this useful tidbit I showed you, when you have 30, 60, remember 1 goes with 30, square root of 2 goes with 3, square root of 3 goes with 60, and 2 goes with 90, right? So that means the side opposite the 30-degree angle is 1, the side opposite the 60-degree angle is square root of 3, and the side opposite the 90-degree angle is 2 in our reference 30, 60, 90 triangle. So what is and also we want to remember SOHCAHTOA. So the sine of 60 is going to be opposite square root of 3 over 2, the hypotenuse. Now, this implies the sine of 240 is going to be, since 240 is a third quadrant angle, and the y value is going to be negative, we're going to get negative square root of 3 over 2 for the sine of 240 degrees. Now the cosine of 60 degrees is going to be adjacent, which is 1 over hypotenuse 2. So this implies that the cosine of 240 is going to have the same value with the sine adjusted. Again, the x is negative as well, so the cosine will be negative. So we just adjust the sine and we get negative 1/2. The tangent of 60 degrees is going to be opposite, which is square root of 3, over adjacent, which is 1. Now, notice tangent is y over x. So even if they're both negative, negative divided by negative is still positive. So the tangent of 240 degrees is also going to be just square root of 3. Let me go ahead and simplify that first. So that's square root of 3, right? This implies the tangent of 240 is also just going to be positive square root of 3, because both sine and cosine are negative. When you divide two negatives, you get a positive. We could have gotten the tangent instead of from the graph. We could have gotten it by dividing these two as well, because remember, tangent is sine over cosine for a given angle. All right, so we have the three main ones. So these are what I'm talking about. So all we have to do to find the other three is find the reciprocal of those. So the cosecant of 240 will be the reciprocal of this, which is negative 2 over radical 3. And we're going to rationalize. So we end up with negative 2 radical 3 over 3. Okay? When it comes to, let me start a little further this way. Secant of 240, that's going to be the reciprocal of this. The reciprocal of negative 1/2 is, of course, just negative 2. Finally, the cotangent of 240 is going to be the reciprocal of the tangent, so 1 over square root of 3, which we will rationalize by multiplying by square root of 3 over square root of 3. So we end up with square root of 3 over 3. All right, so now we just found all 6 trigonometric function values for a 240 degree angle. And we did so by first finding the reference angle. Now, I'm going to show you an alternate to this reference angle scenario, which also works out quite nicely before we move forward. Okay, so the method that I'm going to show you here is not going to really be a different method. It's just a different way of handling the same method. So let me go ahead and completely handle this by hand so you can get a feel for what you'll be doing. So notice that we're dealing with 240, so we know, we already saw that it's going to be around here, right? So we still do need to find the reference angle, right? This angle right here. So we know that it's going to be a 240 minus 180, which is 60. So we can put that in here. So go ahead and make your right triangle like you normally would, right? Now, and what we're going to do is we are going to use our reference 30, 60, 90 triangle, but in a little bit more efficient manner, in the sense that I'm just going to take these numbers 1, square root of 3, and 2, and I'm going to place them on this graph in a very consistent way. So I know 2 is the hypotenuse, that's the easiest one. I can just put that there. So the side adjacent to 60, you see right here, I know is going to be 1, but since the location is to the left of the origin, I'm going to put -1 right there. And for the y value here, I know that I'm going to have the side, well, actually I can figure out this part first because that's opposite the 60-degree angle. So I know it's going to be square root of 3 if this is 2. So, but I know because it's going to be in this location, it's going to be negative square root of 3. So now I know that the point on the terminal side of this angle of interest to me is -1, negative square root of 3, and that's x and that's y. So now I can just go ahead and handle things as I would for any angle using that x and y. So for sine of 240, I'm going to get y over r, which is so it's a more direct approach. You see, we don't have to find the trig functions of 60 and then find the trig functions of 240. This way we just do it directly as long as we adjust for the signs right away. Okay, so we get y over r, right? So negative square root of 3 over 2 cosine of 240 will be x over r, which is as you know, x is -1, so -1/2. The tangent of 240 is going to be y over x, which is going to be negative square root of 3 over -1, which is just going to be square root of 3. And then of course for the other three we just take the reciprocal of these as we already saw. So these are the three main functions, right? Because the other ones are just reciprocals, they're easy to get. So remember, this is not really a different method. We still have to find the reference angle, right? But what's nice about it is it's a more direct approach. So you set up your angle just like before, and you use the reference angle to come up with this point, okay? And that's the key thing to understand. All right, and that should do that. So make sure that you can handle problems such as this before we proceed. Okay, so here's another one. You should definitely try this on your own before you watch the rest of the video. See if you can come up with the trig function values on your own. All right, so here's the nice computer generated version of a 350-degree angle. So you just start here. You know that if you go here, that's 180, 270. If I go all the way over, that's 360. So I need to go 45 less than 360, and I'll stop there at 315. So if you want to do it by hand, that's not difficult either. You just basically do the same thing. You start here, and you go to here, and you stop. So we need to find the reference angle, and we know that this is the quadrant 4 type of an angle. So the reference angle is just going to be the full circle 360 minus the original angle. So to get theta prime, we do 360 minus 315 degrees, so we get 45 degrees, right? So what we're going to do is we're going to go ahead and realize that this reference angle here is 45 degrees. We're going to form our triangle, our right triangle. Do that a little bit nicer. All right, now all we're going to do is we're going to go to our reference 45, 45, 90, right? I can draw it in this way, or I can just draw it like this too. It makes no difference, see? Because now I know that for a 45, 45, 90, I have 1 square root of 2. Remember, we had this little nice thing to help us remember it. That goes with 1 square root of 2. All right, so now I'm just going to adjust the signs, right? Notice that here, this adjacent side over here, that's going to be at a positive 1 location, but this one will be at a negative 1 location. So the ordered pair of interest will be 1 comma negative 1, with the x being 1 and the y being negative 1, right? So now we know that the square root of 2, of course, is not going to change. That's going to be positive. So now we can find the values very easily. So we have sine of 315 degrees. So remember, we're just handling this directly. That is going to be the side opposite. Well, we're actually now using the x and r notation, right? So it's just going to be y over r. What's y? Y is negative 1 over square root of 2. Go ahead and rationalize that by multiplying by square root of 2 over square root of 2. So we end up with negative square root of 2 over 2. Now, for the cosine of 315 degrees, we get x over r. So x is positive 1, so we get 1 over square root of 2. And now we're going to go ahead and rationalize that, and we end up with positive square root of 2 over 2. For the tangent of 315 degrees, what we get is y over x. So it's going to be negative 1 over 1, which is negative 1. The rest, of course, are easy because we're just going to take the reciprocal of what we have already found. So cosecant of 315 degrees will be 1 over the sine, so we need the reciprocal of that. That's the easiest one to reciprocate. So we get negative square root of 2. For the secant of 315 degrees, we're going to take the reciprocal of this. So that's just going to be square root of 2. And for the cotangent of 315 degrees, we're going to take the reciprocal of negative 1, which is of course also negative 1. And that's it. That's how you would handle a problem like that. Okay, so next we want to find the values of the 6 trigonometric functions of a 2100 degree angle. It's, remember, done in a very similar manner. We'll generate the graph of the situation and proceed. Alright, so here's the complex version of the graph of a 2100 degree angle. But of course that we know that we don't need to worry about all this complexity because we're going to simplify the situation. We're going to go ahead and first find a coterminal angle which has a value which is much more easy to handle than this. So we're going to take 2100 divided by 360. We can see there is almost 6, but not quite, full circles hidden inside that. So we're going to take 2100 and take away 5 full rotations to see what we get. 300 degrees. So we know that a 2100 degree angle is coterminal with a 300 degree angle. So we'll go ahead and draw the situation. Now I know that if I start here and go here, I know that's 270. So for 300, I just need to go a little bit further to the right, somewhere around there. All right, so there's the scenario. And remember, that again is not the 2100 degree angle itself, but it's one that for all practical purposes the same because it's coterminal. Notice it looks exactly like the 2100 degree angle as far as the initial and terminal sides are concerned. So again, we're going to form our triangle, but let's go ahead and find the reference angle theta prime first. This angle right here, see how much that is. Remember, this is again a fourth quadrant scenario, so we're going to take 360 and take away the angle, so that's 300 degrees. So 360 degrees minus 300 degrees, that's going to be 60. So again, we have a 60 degree scenario. So if we draw our 30, 60, 90 angle to look like that, look. That's going to be 60, that's going to be 30. I know opposite 30 is in the reference. Remember, this is the reference, 30, 60, 90. So opposite 30 is 1, opposite 60 is square root of 3, and opposite the 90 is 2. So over here, I'm going to get that 2, but remember, this is going to be negative square root of 3 over here because it's below the x-axis. And for the 2 doesn't change, that's just the distance, that's always positive. And the 1 is also going to remain positive because it's a positive x value here. So the ordered pair of interest is going to be 1 comma negative square root of 3. 1 is the x, negative square root of 3 is the y. Now we can go to work, right? See, very simple. It's really simple once you get hang of it. All right, so the sine of 2100 degrees is going to be y over r, so it's going to be negative square root of 3 over 2. Looks very familiar to what we've done already, right? The cosine of 2100 degrees is going to be x over r, which is equal to 1 over 2, positive 1 over 2. The tangent of 2100 degrees is going to be y over x, which is going to be negative square root of 3 over 1, which is negative square root of 3. For the other 3, you're just going to take the reciprocal of those. I'm going to let you finish those so that this video can eventually end. Okay, so there we go. That's how you do that. All right, this next one, of course, is handled in exactly the same way. I just want to show you a pointer. You're going to be doing this. I'm not going to go through all the values, but just a tip. Notice that when we take 1050 and divide it by 360, we get 2.91. But remember, since this is a negative angle, to get to a positive angle between 0 and 360, which is coterminal with it, we add multiples of 360 rather than take away. So we're going to start with negative 1050 and add. And remember, when you start with a negative, you round this up, so to the next whole number. So you add 3 multiples of 360, and you notice that you end up with a 30-degree angle. So the reference, the coterminal angle and the reference angle are both going to be the same, because notice when you have a 30-degree angle, that's going to be its own reference angle, right? So all you have to do is set up your triangle, right? And this is just the basic 30, 60, 90. So you know opposite 30 will be 1, opposite the 60 will be square root of 3, and opposite the 90 will be 2. And then you can just go to work and find all your ratios. You don't really have to even do any adjustment of the signs, because it's all positive, right? You're in the first quadrant. Very, very simple scenario. And that's how you would approach something like that. All right, so now we want to evaluate the expression given here, right? Now, if you're in autopilot mode, you may at this point sit here and go, oh, okay, I'm just gonna draw a figure, figure out where 225 is, set up the right triangle, find the sine and cosine, etc. And that's fine. I mean, you could do it that way. But if you're really awake, you would realize that, hey, we just went over a really nice Pythagorean identity, which said the sine squared of an angle added to the cosine squared of the same angle is always going to be 1. Remember? So that is, of course, going to be true for a 225-degree angle as well. So if you're really alert, this problem takes all of 1 second to do, and you're done. So you stop right there. But again, if you really want to, you can try it. Sit there, do the figures, find the numbers, and you're going to get to exactly the same scenario. Just a quick view of it will show you. Look, 225. This is from here. It's 180. So you're right here. That should look familiar to you by now. So the reference angle is 225 minus 180, which is 45. So you know you're dealing with a -1, -1, square root of 2 scenario, with the point being -1, -1, with the x and y, right? Try it. Use this figure to find the sine of 225. There's the 225-degree angle, which is y over r, and then the square it and add it to the square of the cosine. Make sure you get 1. It's a very, very good exercise for you. These are different angles, so we're not going to be able to get away with a real quick shortcut like the last one, but it's easy. We just handle each one separately, right? So let's just quickly work through these. So let's just do a quick sketch for 60. We know where that is, right here. So that means this is 30. So we have 1 here, we have 2 here, and we have square root of 3 here, right? So the cosine will be adjacent 1 over the hypotenuse 2. So 1/2 squared, don't forget to square. And for 150, right, we start here and we go to there. So you know that for this kind of an angle, to get the reference angle, you have to go 180 minus the angle, right? So 180 minus 150 will give us 30, right? So we know we're dealing with a 30, 60, 90 scenario. So we know that the side opposite will be 1, so that means this point here is 1, and the side adjacent will be which is opposite the 60-degree angle should be square root of 3. So because of the location, it'll be negative square root of 3 there, and therefore the point we're dealing with is negative square root of 3, 1. This is the x value, that's the y value, and of course this will be 2, right? Because it's just a 30, 60, 90 triangle we're looking at. All right, so secant of 150 is going to be r over x, right? Remember, secant is the reciprocal of the cosine. Now r is 2 and x is negative square root of 3, correct? So we get plus 2 over, we don't really need to rationalize it because look what we're gonna do, we're gonna square it, right? It's not gonna make any difference. All right, so if this were a problem in itself that we were doing, we would have rationalized this answer and provided the rationalized answer. But here we're going to be, it's just part of an operation and we're going to be squaring, so the square root is going to go away anyway. Minus. Now we need to do a quick, so this was the 150-degree angle scenario, and now we're going to do a 210 real quickly. So starting here, you know that's 180, so 210, we need to go 30 more. So there is my scenario right there. So I know that the reference angle is going to be 210, take away 180, so it's going to be 30. So I know I'm dealing with a 30, 60, 90 scenario. So I know this is going to be 1, which means this right here is negative 1, the location, and this here is going to be negative square root of 3, and this one is always positive, so 2. So basically the point on the terminal side of interest is negative square root of 3, negative 1. With negative square root of 3 is x, negative 1 is y. So cosecant of, we're dealing with a 210-degree angle, cosecant of 210 degrees is going to be r over y, actually, because cosecant is the reciprocal of sine. So we're going to go ahead and write 2 over y, which is negative 1. So we're going to get negative 2. So we need to take that negative 2 now and square it. Okay, that's it. So now just simplify. So 1/2 squared is 1/4 plus, this is going to be 4 over, remember the negative square root of 3 squared is just 3, so 4/3. Negative squared, of course, is positive, minus negative 2, the square of negative 2 is going to be 4. So now we're just going to put a 1 below that, and we're going to combine those unlike fractions. We need a common denominator of 12, which means we need to multiply this 4 by 3 and also the 1 on the top, the 3 here by 4 and do the same to the top, and the 1 here by 12 and do the same to the top. So now we end up with 3 plus 16 minus 48. All right, so 3 plus 16 minus 48, and we get negative 29 over 12. So that's all there is to it. You just take it one step at a time and it all becomes quite simple. All right, so here's a question given in the form of a true or false, choice kind of answer. And basically, what we're going to do is quickly find out where this angle ends up, then we can quickly answer it, right? So we're going to, as you know by now, we're going to go ahead and take the 1890. We're going to see how many 360s are hiding inside. More than 5, so we're going to start with 1890 now, and we're going to take away 5 multiples of 360, and we notice that it's basically coterminal with a 90-degree angle. So it is a quadrantal angle, right? And it looks, for all practical purposes, like this. This is the initial side and this is the terminal side, right? So we can actually pick any number on the y-axis, any ordered pair on the y-axis to find our results, and 0, 1 is as good as any. Okay, so this being x, this being y, so we know that for an angle that looks like this, because remember the cosine of 1890 is going to be exactly the same as the cosine of 90 because they're coterminal. So the cosine is x over r, right? Now notice, since this is the point 0, 1, not only is y 1, but r, which is the distance between the point and the origin, is also 1. So r is also 1. So we get 0 over 1, which is 0. And the sine of 1890 is going to be exactly the same as the sine of 90, which is going to be y over r. So it's going to be 1 over 1, which is 1. So is this statement true? The cosine of 1890 is 1. No, we know what the cosine of 1890 is. It's 0. So this one is false. How about this one? That the sine of 1890 is 0. Well, no, we know that it's 1. So that's also false. Okay? So nothing to worry about in a situation like this. Just work it out like any other problem. So this is actually a simple equation that we're solving here. We want to find all values of theta in the interval, half open interval from 0 to 360 left inclusive, meaning including 0 but not including 360, for which the following statement is true. Sine of theta is negative square root of 2 over 2. This should look familiar to you by now, right? Notice that's related to a 45-degree angle. If you remember, for a 45, 45, 90 triangle, let me do a better job here. We have 1, 1 square root of 2, right? So sine of 45 is, we can use either of the 45-degree angles and we get opposite over hypotenuse, so 1 over square root of 2. If we rationalize, however, we get square root of 2 over 2. So we're looking for relatives of a 45-degree angle as we go around the circle once. So let me just go ahead and do a full circle here. But we want the ones where the sign is negative. Remember, sign is negative where y is negative, right? Because remember, sine of theta is y over r, right? Since r is always positive, sine is only going to be negative if you have negative for y over positive, which will give us negative. So that is only, so what relatives of 45, which is right here, right, are going to have that quality? There is one here, right, and there is one here. So we just need to remember what those are. Now that's easy, because remember, starting here, that's 180, add 45, so what will it be? 225. And this one, remember, all the way here is 270, add another 45, and you get what? I believe you get 315. Let's just be sure. So 270 plus 45. See? 315. So what are the two angles or values of theta for which the sine is negative square root of 2 over 2? They're exactly these two. Okay? Because remember, they're going to have the exact same trig function values as 45, except their signs will be different. And remember, since you're looking for sine to be negative, you're going to want to look for relatives of 45 which have a negative y value associated with them. So they would be exactly these two locations. Here's a similar problem, but this time we want the tangent to be 1, right? We want the values of theta in, basically going around the circle once, right? Doing one full cycle, looking for angles whose tangent is 1. Remember, the tangent is going to be 1. That means sine of theta over cosine of theta equals 1. Why? Because remember, tangent of theta equals sine theta over cosine theta. So notice, if I write the 1 as 1 over 1 and we cross multiply, that means we're looking for the places where the sine of theta equals the cosine of theta. So where does that happen? That happens in two locations, and they're both related to what? Remember, the only angle we have discovered for which the sine and cosine are the same is a 45-degree angle, because we have considered this 45-degree angle. What's the sine of that 45-degree angle? It's going to be 1 over square root of 2, right? And what is the cosine of that 45-degree angle? It's going to be adjacent over hypotenuse, so that's also 1 over square root of 1 over square root of 2. And what is the tangent of that 45-degree angle going to be? Opposite over adjacent, 1 over 1, so it's 1. So we know the angles we're looking for are going to be related to a 45-degree angle. So what relatives of 45-degree angle would give us a positive 1 for tangent? Notice that can happen whenever sine and cosine are the same, and that happens in two locations. One is there and one is there. Here, because both the x and y are positive, right? And here, because they're both negative. So in both of those locations, we would end up with a positive tangent, and because they're related to 45, the tangent is going to be 1, right? So the two angles that we are interested in, one is going to be 45 itself, right there. The other one is going to be this one, which is, remember, just 180 plus 45, which is what? 225. So those are the two angles from between 0 and 360 for which the tangent is going to be 1. Alright, so here's a nice little problem which we should be able to handle. Now, we want to find the coordinates of this point P, the Cartesian coordinates for that point on the circumference of this circle that we see. and they're telling us that this angle is 120 degrees, right? Now, notice that if I go ahead and draw that line, right, to create the y-axis of sort, right? Notice that means since this much is going to be 90 degrees, that's going to make this angle 30 degrees, right? So if I go ahead and drop a perpendicular here, right, I'm basically going to be looking for this value here and this value here, right, x and y. Now I do know that this angle here is going to be 60, right, because this is 90 and this is 30. So if I look at my reference 30, 60, 90 triangle, right, I know that opposite the 30 I would have 1, opposite the 60 I would have square root of 3, opposite the 90 I would have 2, right? So first thing I'm going to do is find the magnitude of x and y, then I'll adjust for the sign. So I know that x is to 1 as 4 is to 2. I'm just setting up a proportion because those are similar triangles. So we get x equals 2. Now I know y is going to be to square root of 3 as 4 is to 2 as well. So if we cross multiply, we get 2y equals 4 radical 3, so y equals 2 radical 3. So now all I have to do is adjust for the location, right? So notice that here we're going to have a negative value for x and a positive value for y. See? So the x will be actually -2, and the positive y value there will be 2 radical 3. All right, so one thing that we have to assume here is that the center of that circle is 0, 0, right? So as long as we assume that, that's going to be the Cartesian coordinates of the point P on the circumference of this circle. All right, so I believe you've had enough, right? Well, I know I've had enough, so let's call it the day. That should get you through this set. I know it's a rather long set. Sometimes these sets just work out this way. There's just a lot of information that needs to be conveyed, so we don't mean for them to get this long, but they kind of don't make sense if you split them up because they're so related to each other, right, the concepts. So but anyway, we have finally reached the end. Congratulations if you've made it this far. And again, this all needs practice, so you want to make sure you're staying up to date with the homework, and I will see you in the next lecture. Stay safe.